All right, so good evening, everyone, and welcome back to another lecture for cloud computing for the winter 2023 semesters. Uh, in the previous classes, we have started off our discussion regarding the first learning module, which was essentially to get an understanding of the basic terminologies and some of the fundamental concepts that revolve around cloud computing's background, right? So what was the important takeaway from those discussions, if you would like to, put it that way, was basically the shift of paradigm and how we started off versus how we got to the point where we ended up with cloud computing itself, right? So again, as I had talked about this in the course overview lecture, it is always beneficial to get an understanding of where we are coming from before we start playing around with what exists in this current day and age, right? So later on, as we venture into the AWS platform, trying to understand the different services that AWS provide with respect to, let's say, storage, or with respect to, let's say, authentication, identity management, key management, so on and so forth, databases, and those kind of things. It begs the question first for us to learn is that where or how did people come up with the ideas for developing such an architecture and then providing that as a service? That is basically to say that cloud computing typically is known as, when you think of cloud computing, it is known as either service computing, right, or utility computing. So another way to understand this is basically you pay for whatever you have used. Okay, so this was the idea, or this is the idea behind cloud computing. And all the services that are set up is basically set up with this idea in mind. So if you think from an architectural perspective, right, if you think from a software perspective, not like a software, but in terms of services perspective, then this is known as utility computing. Now, when we started off our discussion in the first lecture or the second lecture, when we were discussing the overview of the course and the first learning module, the main takeaway from that discussion was the shift in paradigm. Okay, basically, when computing started, when the architectures for these kind of computing were being developed, what was at the very beginning? So remember, there were two different spectrums of these utility or service computing, right? The current day utility or service computing, there were two different type of tasks that was performed or executed by different groups of people, right? So the first one was categorized into the idea of high throughput computing. And then the second spectrum, or the other end of the spectrum, was basically high performance computing, or HPC, right? So the idea here was to execute complex engineering problems, which was going to take a long period of time, right? So in other words, you would be familiar to this terminology as batch processing, right? So you have a very big task. Let's say it's a simulation problem of some kind of engineering domain, biology, chemistry simulation, and things like that. Or it's some kind of maintenance task for, like, let's say, financial institutions such as banks, where they're performing like a monthly audit of their whole system, bringing things together, applying different scripts, logic in order to perform analysis and things like that. So that is high performance computing. And the main feature of high performance computing is basically the fact that it is computationally intensive, right? So this was one of the main features of HPC. And then on the other side of the spectrum, you had high throughput computing. Now, the advent of high throughput computing is directly related to the popularity of the World Wide Web as a service. Okay, remember, all of this is running on top of an infrastructure that we know as the internet, right? And then on the internet, there is a service that is deployed that is the World Wide Web. www is the service itself, right? And then people use the setup of that www service in order to kind of develop their own services that relates to their own business logic, and then provide that to the users using the internet as a platform, right? So when the browsers became more and more famous, and it became as a medium of kind of dispensing these services, or a way to access these services that different developers were creating, right? So the goal changed from the idea of batch processing or high performance computing towards satisfying more and more user requests, right? So one of the more common services that became very popular that falls into the category of HTC is something called web search, right? We are all familiar with that. But back then, around the 93s, 94s, that was up and coming, and it was becoming more and more popular, exponentially popular, right? And when you think of a service like that, it is not about the usage of the computational power, right? It's not about the performance that is the important criteria there, but it is more along the lines of how many user requests can you satisfy as a service provider over a unit time. Now, how you define the unit time, that is up to you. So their latency became one of the key important features, right? So that is where the throughput aspect of HTC is coming from. So these were the two fundamental approaches of computing architectures that came into being. And from here, things started to take a turn, right? More and more different kind of new computing paradigms came into the picture, right? And people started using that depending on how the evolution took place. So from high throughput computing, we learned about the fact that P2P came into being, right? File sharing that we know as the inherent file sharing. And then the high performance computing gave rise to the idea of parallel processors, and then parallel processors led to the origination of computing clusters, which is basically the topic of focus for the first half of the learning module that we are discussing right now, okay? And then eventually, when people merged the idea of file sharing and computer clusters together, that gave rise to grids. And if the grid was oriented towards a computer cluster architecture, then that was basically a computational grid, that it is focusing on high performance computing based tasks. And then if it was leaning towards the P2P architecture, the grid, then that was basically a data grid for sharing data, for holding data, and then dispensing, let's say, multimedia files and things like that. So for now, not for now, in this day and age, that data grid has a different name and shape, so to speak, right? So if you're familiar with the word CDN, or content delivery networks, right, which is also something that is supported by cloud computing infrastructure as well, whether it be Amazon, Microsoft, or Google, everybody has their own CDN architectures, right? So that is essentially a more evolved shape of the initial data grid that came into being, right? So that is what was going on, or that was the whole background of data grid versus what it is right now. And then applying some specific technologies. So for example, if people, when they applied sensing to computational or data grids, that gave rise to Internet of Things infrastructure. Now, in the previous lectures, which I shared, there was a discussion on the difference between IoT and CPS, right? And this is a very hot topic of debate, right? Some researchers in the academia believe that the aspect of IoT is, well, how to put it politely, not something that is grounded in fact, right? And everything is kind of CPS, while some others do believe that there is still a distinction between IoT and CPS. But essentially, if you kind of try to read between the lines and dig a little bit deeper as to like, oh, whether there is a difference between Internet of Things and CPS, one of the subtle differences that you might be able to point out is the fact that the IoT is mostly focused on the interconnection of the sensing devices, whereas CPS specifically focuses on the logic that will help you to execute the control of the physical infrastructure from a cyber platform. So that is essentially the subtle difference, if you want to kind of put your finger on, right? But you see, in this discussion, if you pay attention to what we are talking about here, that IoT is about the infrastructure, the interconnectivity, and then CPS is about the logic that allows you to actuate the physical world, right, through the cyberspace by writing programming and logic. This is where the problem with the debate, or this is where the debate is coming from, right? Because if you think in terms of interconnectivity, are we going to leave it at that? Right? Ask yourself this question, is that if you are connecting up a network and you cannot dispense any services on that, right? Then what is the point of that network? That's just going to sit idle, right? And if you look at the current literature, in academia, or even if you go to the industry, right? People do talk about IoT applications, right? People do talk about how to actuate, let's say, the HVAC system, different concepts such as smart cities, autonomous vehicles, industries, industrial control systems, those kind of applications, they are discussed within the branch of IoT. So that's, you see, that is where the push for that debate is coming from, that, oh, if you're saying that IoT is about the interconnectivity of the network, but then you're talking about the application itself, which is about controlling the physical sensing infrastructures through logic, right? Then where does CPS fall? So this is the reason why people say that, there is no distinction between IoT and CPS. So kind of something to keep in mind, that this is where that debate is coming from, right? And similarly, if you take the grids, right, the data and the computational grids, and if you put the idea of virtualization to it, then you get the formation of the modern day cloud computing. Okay, it's not complete, and there is a reason why it is not complete. Virtualization, yes, no doubt, is the backbone of modern day cloud computing, right? But just with virtualization, you cannot really unlock the potential of what cloud computing provides. Cloud computing is not just built on virtualization. There is another aspect that is involved. And later on, when we learn more and more about virtualization and then close the gap towards reaching the point of actually discussing cloud computing infrastructure, we will see that there's another sibling of virtualization, which is a little bit lesser known, but it is known as elasticity. Okay, and elasticity, along with virtualization, actually forms the backbone of modern day cloud computing. All right, and then if you add on this different things such as services, RESTful APIs, and things like that, those kind of logic, right? That gives you the backbone of the modern day Web 2.0. It's no longer 2.0, it's almost reaching 4.0 at this point of time. But that's how the Web 2.0 services, the microservices that and things like that, that came into being when you are applying SOAP architectures, Spring frameworks, and then things like RESTful APIs into the picture, and then applying it on the grid and then providing that as a service, right? So this chart essentially is something that you need to be completely familiar with, okay? And the question that we have is basically, what is the definition of virtualization in this context, okay? So let's talk about those two things, and elasticity as well. So think of virtualization this way. Let's talk about the backbone definition first, and then we will talk about the exact definition of virtualization when we go to the next chapter, which is specifically talking about virtualization, right? So virtualization in its most bare bone form, try to understand this, right? So let's say I have my computer right now, all right? My computer is, for example, hypothetically speaking, has a processing power or compute power. Okay, I'm not going to call it RAM, because we don't call it RAM in this particular instance, but we call it processing or computing power, right? So I have 32 gigs of processing power. And then let's say I have a storage, not memory. Memory is basically the RAM itself, of around, let's say, 1 terabytes. Okay. So now if this is the situation here, and let's say running my specific applications, whatever I need right now, I'm, let's say, running Zoom here, I have a PowerPoint going, background, maybe a video editing software is running, some database servers are running, etc., whatever. So compute power, and this is also called memory. Okay, just to be familiar with the terminologies. So let's say by running those applications on my computer, I am essentially using 8 gigabytes of memory. Okay, so now what I have left with is around 24 gigabytes of memory. Okay, give or take. And from this, let's say 8 gigabytes of memory is also used by my operating system. Let's just assume that. So what I'm left with is 16 gigabytes of memory, which is basically idle. All right. So now, essentially, can we create a virtual environment? And by that, I mean a system within a system, okay, of that is going to share some of these idle resources, and that can be provided as a service if you want to, or for free, to other users to have them run their applications on the system. So let's say you have some kind of data analysis job, right? But you don't have 12 gigabytes of memory in order to run whatever application that you have. But I have that memory. So what I can do is I can create a sandbox kind of environment, right? So basically like a box which has its own, which is sharing the underlying computing power of the parent device or the physical device. And then it is also sharing some of the storage if you need it. If you don't need it, that's a different story, right? And then allow you to deploy your application within this sandbox environment. And this sandbox environment can run its own specific operating system as well, right? So for example, if the parent device is, let's say, running Windows, and you specifically need, let's say, Linux, or you specifically need some kind of Mac OS to run your application, right? Just for the sake of discussion, if we assume this, right? Then this sandbox environment that I create can be loaded up with the operating system of your choice. It will share the available idle resources of the underlying physical computer. And then if you need some storage, then I can also provide you with some storage depending on how much of idle storage. Let's say I have like 500 gigabytes of free space left, which I'm not doing anything with, right? So I can provide you with, let's say, 256 GB of storage to the sandbox, and then whatever the outcome of your visualization or analysis task is, that is going to be returned back to you, right? So if you're familiar with these applications called VMware, right? So this is basically a virtualization tool that is available for individual clients, okay, free of cost. There's also a commercial version of it if businesses are using it. So this allows you to create this kind of virtualization environment, right? Just a second, Sal, I will come to your questions. So essentially, this is what virtualization means, okay? You create something like a sandbox environment, and then within that environment, you kind of set it up in such a way that will allow to meet the demands of the client, and then also allow the provider, which is me in this particular example, to utilize the idle resources that is sitting on the physical machine. Okay, and when we discuss computer clusters in a little bit, right, we will see that discussion as well, that slowly and slowly the aspects of virtualization started, kind of creeping in to the architectural design of computer clusters, and people became more and more fascinated by it and saw it as a potential to kind of make the utilization of idle resources more efficient, or to pool resources together. Okay, so that is also something that is doable. So another example for pooling the resources. So this example that I gave you is specific to utilization of idle resources. That is 16 GB of memory was sitting idle. There's storage space that is sitting idle, and I'm making effective use of my idle resources. But there is also a concept of pooling resources for parallel tasks. Okay, remember in the last class, we discussed about all these definitions of what is centralized, decentralized, distributed, and parallel computing. So I hope everybody remembered that. Right, so let's say you have a task, a high performance task that can be parallelly broken down into different segments, assuming that there is no data dependency or instruction dependency between them, right? So what I mean by that dependency is that one task is not waiting to execute itself till another task finishes and provides it with the data that it needs, right? If you have that kind of dependency, that is a very impeding factor for parallel programming, right? But for now, assume that you have the most ideal situation and you have, let's say, a very large chunk of task, which was broken down into, let's say, 4 different segments, right? And this needs to be executed parallelly. Now, depending on the processor architecture that you're using, right, it can provide some kind of bottleneck to execute all these 4 different tasks of this one single task parallelly at the same time, okay? And on top of this, let's say you do not have the sufficient resources on your computer, your parent computer. Let's say your computer is just 8 gigabytes and it doesn't have the sufficient memory in order to run 4 tasks in parallel, right? Let's say each of these tasks require 4 gigabytes of memory. So you need around 16 gigabytes of memory. So one of the option is you can send me these 4 different tasks. Instead of sending a single task, you send me the request of 4 different tasks. And what I do is I break down my idle resources into 4 different sandbox machines because I have that resource. Okay. And as a result of that, if I break down the 16 GB into 4 gigabytes of sandbox or virtual environments, then I can run all of those 4 environments in parallel to finish your tasks and then get the data at a much faster time compared to running these in sequential order and then getting the results one by one on your own machine, right? Because remember, for every machine, you cannot use whatever RAM is given to you. If you have 8 gigs of RAM, you don't have access to 8 gigs of RAM because the OS needs a little bit to run its host applications and stuff like that. So you can't really use that. So you have to keep these things in mind when you are doing virtualization, right? Even if, let's say, I did not have 16 gigabytes of RAM that was available to break down these 4 different tasks into 4 units of 4 gigabytes RAM, that's what it means. Let's say I just had 8 gigabytes of RAM. If in my network or in our network, let's say if some other student had a little bit of processing power that is left, right? So they can also provide a virtualized environment. So what can be done in that kind of scenario is you can essentially pool the resources together in order to execute a task that wouldn't have been able to be executed in parallel, let's say, or in concurrency, if you had executed that in your own parent system. So that is basically the idea of virtualization that gave rise to the concept of cloud computing. This thing that we just talked about here, right? On this slide, that when you applied the concept of virtualization to either computational grid or data grid, right? Mostly about computational grids, then that gave rise to the notion of cloud computing. And the second aspect is basically elasticity. Now, elasticity is something that we will discuss specifically once we cross virtualization domain and move into specifically discussing about cloud computing architecture, right? So elasticity, if you take the literal meaning, right? If you think of an elastic band, right? So let's say you have this elastic band. Everybody's familiar with an elastic band? Yes? Okay. You can use emojis to communicate with me, by the way, if you are not comfortable speaking up, so that I know that somebody's there at least. So, all right. So let's take an example of an elastic band. All right. So elastic band, rubber band, whatever you want to call it, right? What happens when you stretch it? So if you pull an elastic band, right, it basically elongates itself up to whatever degree it can, depending on the material that you're using. So think in terms of physics. When you're pulling it from these 2 directions, what are you applying to it? You can call it some kind of force, right? You're giving it a force, and that is because that is the reason why it is becoming elongated. Or you can think of a different term. You're applying some stress to it, right? And that stress is basically allowing it to respond to that stress and become larger, right? So now if you take this analogy and if you apply that to the computing domain, right? So let's say initially you have a web server. Okay, so let's say you have a web server that is currently running on 4 servers. It is running 4 different servers. Okay, not say a web server. Let's just say you have a web application that is running on 4 different servers. Okay, and it is supporting about, let's say, 200 users any given day. For some reason, your application becomes very famous. Okay, overnight, let's say you go from an unknown brand to a very known brand and people start flocking towards your server. And then these number of users, these 200 users, let's say in a span of 48 hours or so, or maybe during Black Friday, let's take that example, it will be more. Let's say Black Friday comes, your platform is giving a huge sale and more and more people are coming and visiting your web application, right? So instead of the everyday 200 users that you handle during that period of Black Friday sale, your users just go from 200 to, let's say, 20,000. Okay, overnight, just for that 2 days. So if you try to balance out these 200 users, so initially how many users were being, if you balance out the load, right? So we're talking about stress, then stress can be also thought of load that is being applied here in this particular case. So if you have, let's say, 4 servers supporting 200 users, how many users per server if you balance it out? 50, okay? But now, if you try to balance out 20,000 users with that same 4 servers, you will see that this number will rise by a lot, right? How much? 5,000, okay? So that is an increment of what? Over 100 times. That's a 100 times increment that has happened. So this is going to apply stress to your existing servers, right? And if that increases the capacity of what these servers can handle, then what is required is for you to, let's say, go down for 5,000. And let's say your company's policy is that every server that is hosting your web application, the threshold that is going to be there is, let's say, I don't know, 100 users per server, in order to ensure the latency that is maintained by your service, right? You have decided as the service provider that no more than 100 users at any given point of time should be supported by any of the servers that is deployed. So basically what is happening now is that we have to bring this 5,000 to 100 now. So that will require us to do what? That will require us to, the solution for that is to deploy more machines, more servers. And how many, if I may ask, real quick, somebody give me the number. So I have 4 servers, 50, okay. Okay, so that means I have to take these 4 servers and I have to add 50 more servers in order to make sure that I am within the threshold of my client. And the reason why I say client is because if I am the service provider, then I have to ensure that I meet the threshold that has been set by my client, who is the service provider for their users. So there is something that is going on here, is that service provider for users are basically the client to the people who are going to provide the infrastructure that will allow the service provider to host their application, right? So just be aware of these subtle differences in terminology that I will be using throughout, right? So essentially, if you now go back to this discussion that we were having, that what happens if you take an elastic band and then put stress to it, it needs to kind of extend itself. So that's the same thing that is happening here as well, that if you apply stress to an existing platform, then it should be able to scale by itself. That is the important term here, that it should be able to scale by itself. So that means I, as the infrastructure provider, should not be manually responsible for taking these 4 servers to around 50 servers. The service provider, who is actually responsible for providing service to the user, they should not be worried about it. Neither should the user see any kind of latency to the service that they are available. And that is the concept of elasticity, which is the dynamic scaling up and down. So remember, when we talk, or when you are going to read different literature on the topic, basically the category is scalability, this discussion that we are having, right? And scalability has scale up and then scale down. Okay, there is also a separate category here, which is known as scale out. But we are not going to be discussing that right now. We are focusing mostly on scaling up. So there are 2 types of scaling that can happen. It's a vertical in nature, which is scaling up. And then there's a horizontal scaling, which is specifically related to the actual hardware that you're adding to your infrastructure. That is known as scaling out. Okay, so this discussion is not about scaling out. This is mostly about scaling up, right? So now let's say you have figured out a way. Okay, let's just assume as a black box discussion that you have figured out a way for taking this 400 to 50 whenever you see the threshold number of user is crossing the client's request, right? The client has requested that no server should have more than 100 users at a given point in time. So as an infrastructure provider, I can write a script. Okay, you will see later on, you can essentially actually write a script that can automate the process of this scaling up, right? And take 4 servers to 50 servers during the Thanksgiving thing, right? But that is not the full definition or the full scope of elasticity. Elasticity also requires that when I remove the stress, then this elongated band should come back and retain its original form, right? And that is dynamic scaling down as well, which essentially means, with respect to our discussion, is that eventually when Black Friday sales are over in probably like, let's say 3 to 7 days of time, and the user base goes back from 20,000 to around 200 users, then this 50 servers that were added to support the threshold that the user provided needs to go back down to its original level of 4. So that is the concept of elasticity. That is, when you're putting stress on this computing platform, it will be able to accommodate you depending on the availability. And when you remove that stress, those resources that were added to accommodate the stress should be taken away, and the original form of the service should be sent back. Okay, so that is the whole idea of virtualization and elasticity, which this forms the backbone, right? So we will discuss more and more of these two concepts as we move more and more into cloud computing, right? So I need to find another question here. Okay, so there was another question when we were talking about virtualization somewhere here with respect to idle resources. So the question is basically, is there any threshold protocol in space or in place, okay, which leaves some idle space empty in order to make sure that your parent computer can accommodate for any spike in demand from one of the virtual hosts that is there, that is one of these sandbox, or we can extend this idea and we can think of what happens if the parent computer needs that as well. Okay, so now to answer that question, this is subjective in nature. All right, so that means if any resources are available, then you can provide that as an empty resource or as a cushion in order to make sure that you can meet the spike in demand from any of your virtualized hosts or yourself. Or if you choose to go, guns blazing, then you don't leave anything empty. Then in that situation, if you hit a deadlock, you will basically hit a deadlock. Your computers will freeze if you go above the allocated space or computing powers that has been given. Okay? Does that answer your question?
Yes, it does. Thanks.
Yeah. All right. Sounds good. So elasticity, we will talk about this when we discuss more about cloud computing. But for now, you need to know that whenever we deploy any kind of resources, okay, whenever we are setting up these virtual environments, right, where we discuss that how much memory are we going to provide, and then how much storage space are we going to provide, those kind of things, that is basically done through with the help of a script file. Okay, I hope you understand what a script file is. Basically, it allows you to automate certain tasks. Okay, it consists of a set of commands that is executed. And once it is executed, then these virtual environments that we were discussing here, which has its own operating system, which has its own computing power, some storage power, and things like that, they are basically started up, right? They are executed or implemented, and then the host is given, or the guest is given access to those virtual environments. Within that script process, there is also a section or a set of fields that asks you what is the minimum number of servers. Let's say if you're speaking specifically with respect to this particular example, if you're deploying a web application, then there is a field that allows you to specify what is the minimum number of web servers that you're going to deploy, what is the desired or the average that should be there, and what is the max. You can also specify, in addition to this, if you are applying something that is known as a load balancer, which essentially monitors. It's a tool that is provided by the infrastructure provider that monitors how many users are being supported by each of these servers. You can also provide a threshold for that, and you can say that no more than 100 requests should be handled per server. So when you execute that, there is this software that is owned and developed by the infrastructure provider. Essentially, these are cloud service providers when we think of infrastructure provider, and that monitors all the servers that are deployed. So you can either choose to say what is the actual number of servers you want to deploy if you have an understanding of user requests. If you do not have an understanding of your user requests, then you can specify how many user requests per server that you're going to handle. Okay. And based on that, the softwares that infrastructure providers have, they monitor these aspects and take care of elasticity. Does that make sense?
I had a question.
Yeah.
Assuming that you have this paradigm with the 20,000 users up from 200, what happens if the things that you set as your load balancer, your min, your max, top out at 10,000 users? What do the rest of the users get? Do they get lag? What happens there?
No, so the cloud is going to add the resources that is required in order to meet the growing demand and later on charge you for that.
Okay, but you said that you can have a max number of servers that
that is what the client can specify. But if you go beyond that, the cloud is going to support you because the cloud is always going to have the community resources. So maintenance is not your responsibility when you go to a cloud service provider, right? So essentially, if it reaches the tipping point, which is what you specify with your question, then the cloud is going to take care of that, even though the client was not essentially aware of. Right? But once it is over, they will charge you because you have essentially crossed the SLA agreement, service level agreement, where you said that this is what I want, right? But elasticity is a functionality that is provided by the infrastructure provider. The reason I keep on saying infrastructure, not cloud service provider, because this aspect is also there in computer clusters, but not as well formed as in cloud computing, right? But so take it interchangeably. But the cloud is going to take care of that. That's basically the idea of elasticity. That is what makes cloud computing more reliable, so to speak.
I still don't understand 100%. So from the perspective of the customer, that makes sense. But like from the perspective of like whoever owns these servers that are supporting the cloud service. So what if there's no more resources to give?
So, okay, in this day and age, it is very rare that you are going to see yourself in a situation like that as an infrastructure provider. Okay, so that is the answer to your question for currently the infrastructure that we have. Okay, they have a vast number of resources that is out there, and the likelihood that they will run out of resources in order to manage your stuff is going to be very little. Secondly, let's just assume for the sake of discussion, they do hit that, upper limit. If they do hit that upper limit, then the only thing that we can do or hope for here is basically trade-off, okay? And the trade-off is going to be in terms of latency. So some users are going to see the lag. And this holds very much true for practical situations, is because we all know that some websites have gone down at the increase in the user request or user activity at a certain point of time. We are all aware of these, right? Ticketmaster is there. Recently, Ticketmaster went down. Is anybody familiar with that? So Taylor Swift released her tickets, and then Ticketmaster just went down because there were so many users who came in and tried to get the ticket at the same point of time. The spike was so sharp that the servers were not able to handle it, right? So then the question is mostly about availability. For any cloud service provider that you look at, right, whether it be AWS, whether it be Azure or GCP, the Google Cloud Platform, they all kind of promise in their service level agreements that they're going to provide you with an availability factor of around 99.999 something percent. Okay, so given that agreement, that is basically a binder which binds the infrastructure provider with the client, which is basically the actual service provider. The chances of this happening is going to be very slim, but in the situation that it does happen, then you are going to see some latency on your website. And in the worst case scenario, your website is going to go down. Does that answer your question? Does that go?
Yes.
Okay. Okay. So that's the whole idea. All right. Of these paradigms. Now, let's kind of trace back again, and come back to where it all began. Okay. So it's kind of like a storytelling, but a little bit boring than our Netflix stuff. So anyways, so where the motivation of all of this came from is to basically take these high performance computing jobs, which was designed in parallel, and make sure that we can make these execution of these tasks scale and allow us to use the concepts of parallel and distributed computing. Okay, so remember, there are three things that you're going to be seeing here. Well, parallel computing, everybody understands. It's like you take a program or you take a task and basically chop it off and allow it to run concurrently. Okay. However, the three things that you're going to be seeing very often here is the concepts of centralized computing, decentralized computing, okay, and distributed computing. So let's take a very, boiled down definition, high level of these three things. So in our head, whenever we see these terms, it clicks what we're talking about. This is with respect to administration. Where is the administrative entity present? So if you have a bunch of nodes, computer nodes, which are all connected together, okay, then where is the administrative entity present? Is it being administered by one central entity? If the answer to that is yes, then that is essentially centralized computing. If these computers are being monitored or administered, let's say locally or in clusters, okay, in different locations, but they all have different administrative entity, then that is decentralized computing. Okay, whether they are geographically separate, that is physically if they are present in a different location or not, that is not the question here when it comes to centralized and decentralized. So this is the important distinction factor from centralized and decentralized to distributed, is that distributed, these nodes are geographically separate, right? They are present in different physical locations, and then they are doing processing of different tasks, and maybe they're pooling it together, or maybe they are, dispensing the service requests of users in that geographical area in order to reduce the latency. Does that make sense? So make sure everybody understands these three different definitions and terminologies. Decentralized is not the same as distributed. Centralized versus decentralized is a question about autonomy. That is, who dispenses the administrative tasks for these interconnected nodes, or basically a network, right? Whether the nodes in the network are present in a single physical location, or they are, spread across a vast geographical domain, not of concern. That is not what we are trying to figure out here when we are trying to discuss centralized versus decentralized. You can have 3 nodes in California, 5 nodes in Georgia, 10 nodes in Michigan, but they might be administered through Michigan, right? All of them report back to Michigan. That is centralized computing, essentially, right? However, if you take that central computing, that administrator in Michigan, and they distribute all the tasks to these 3 different regions, then there is an aspect of distributed computing involved there, right? So don't get confused between these terminologies. When it comes about the discussion of distributing the processing across nodes, which are geographically separated from each other, that is distributed computing. When it is a question about who monitors, or where the monitoring is happening, or where the administrative tasks is being dispensed from, then that is a question about centralized. That is, one node has full autonomy over everybody else, right? It's like Lord of the Rings, one ring to rule them all right? And then otherwise, you have decentralized when you still did not build that single ring, you had 7 rings, and then people were kind of ruling each other, right? So hope that clarifies the situation a little bit, okay, for those who resonated with that example. For those who didn't understand, don't worry, use the actual example that I gave you, all right? So essentially, when people started to build these computer clusters, the whole idea was to take these parallel tasks, right, and make sure that they are scalable, and then distribute these tasks across all of these different nodes that are there, and then the scalability can actually be realized through that execution, right? So essentially, what computer clusters then came to be is basically a collection of interconnected standalone computers. So that means you can think of a computer cluster. If you want to build a computer cluster, you can think, let's say, Oakland University has a set of computers, then Wayne State has a set of computers, then let's say MSU has a state of computers. And then if you just interconnect these different clusters, what you get is basically a computer cluster, right? So that is basically the interconnected network that computer clusters were aiming for when they were initially being developed, right? And the whole idea was that these will cooperate amongst each other. So there is some aspect of distributed computing that was involved in order to create a single integrated pooling resource. But there is a cautionary note on this single integrated pooling resource. Is just, let's say, if I have 3 computers here, right, 2 computers here, and then 1 computer here. And let's say each of these has, let's say, a memory of 2 gigabytes. This has a memory of 4, and this has a memory of 16. So if, yes, the proximity of the nodes does affect the latency. It does. Even if you have it in the same building, if the interconnectivity between the nodes require a larger length of wire, right, even that has an effect on latency, not just its geographical distance. Okay, so basically the question that I'm asking, for those who are not aware, is basically, does proximity of the nodes get affected by latency, although all are serving the same location? It does. Even if they're in the same room, big server rooms in data centers, if they're too far away from each other with respect to its interconnectivity, that also has a little bit of effect on the latency. Okay, so coming back on this discussion, if I have this, so this is total of 8, 8, and then there is 16. If I interconnect them to form a computer clusters, the resources that you get is not additive in nature. So that means you're not going to get an entire 32 GB. There is going to be some loss involved, depending on latency, depending on how much resources are required for the individual clusters, how these clusters are set up, and so on and so forth, right? So you have to keep this in mind. So what we are executing here through computer clusters is basically known as job level parallelism. Okay, if you go back to our discussion, if you don't remember this, if you recall the discussion which we had in the previous lecture, the degrees of parallelism. So we had instruction level parallelism, data level parallelism, and we had job level parallelism, right? So job level parallelism is what we want to execute through these computer clusters, right? We take a job, we divide it into smaller subtasks, and we assign that to the different nodes in either the same cluster, or we distribute it across the different clusters. That is a part of the interconnectivity that we have, right? So the basic architecture that we end up having for computer clusters in that sense, and well, this essentially kind of forms the backbone. Okay, this is where we started, right? And cloud computing started to mimic this later on and added its own benefits of virtualization and stuff like that, and made it what it is today, right? So you essentially have parallel applications. So that is for scalability purposes. Sequential applications, you can't do anything, because as the name suggests, right, it is sequential in nature. One has to wait for the other to finish so that it can be executed. So the main objective, or the main benefit that we wanted to have, was from these parallel applications, knowing the fact that this can be broken down and then distributed across different, computing resources to execute them faster, and then scale it, right? So if you have more nodes in the cluster, then you can distribute it across more computers, and you don't have to wait for the previous application to finish in order to continue the executions, right? So essentially, these were this was the motivation behind setting up these computer clusters, right? And then you had all these different commodity hardwares, and this is the drift from the earlier architecture of high performance computing. So remember, earlier architectures of high performance computing were using supercomputers. So what happens here is that if a given supercomputer, which we all know used to take up an entire room to set up, if that ran out of resources, adding another actual physical supercomputer to the picture was very tedious in nature, right? It was a difficult task. However, when the notion of computer clusters came into the being, right, we no longer started using supercomputers, but we were using what we call as commodity hardware, right? So that means everyday regular PCs or workstations that was affordable, that a lot of individual users would have. We basically started to pool those resources together and connect them through either the LAN, the WAN, or the CAN, and things like that. So we brought them together. Then we connected them together with the help of a network switch, right? Which essentially the LAN is done through, right? And then in order to kind of allow the users to collectively access these resources that are now interconnected with each other. So there's a lot to unpack here that is going on. Okay, and that brings us to one of the most important pieces of the puzzle that helps us bring all these together. So what we are saying here, if you look at this discussion or this point here, so we are looking at a single integrated computing resource pool. All right, so what does this mean? Essentially, the idea of this phrase is the fact that, let's say here in this example, you have 4 different PCs, right? So when a user comes to submit their job request to this cluster, they should not be aware of the fact that there are 4 different PCs, actual physical machines, that are present in this cluster. Okay, so this is the idea. Eventually, what cloud computing uses, the feature that cloud computing has that implements this is transparency, right? Transparency from the perspective of the user. That is, the user is not aware of the underlying infrastructure that is present, right? And the question that comes thereafter is, how do you implement that? And this is the most important piece of the puzzle towards the implementation of the cloud computing architecture. Is the implementation is done through the help of what we call as middleware, which is nothing but a software that uses this concept of single system image, okay, and then makes the availability of the infrastructure transparent to the users, right? So this middleware is basically the administrator. This software is going to allow the addition of new physical machines, removal of new physical machines, decide the creation of virtual environments in each of these physical machines, decide which user's task needs to be sent to which physical machine that is in the underlying infrastructure, and things like that. So if you get the drift of the discussion that we're having, this middleware, again, middleware is basically a software. And to give you a peek, in the domain of cloud computing, this middleware is known as the hypervisor. If some of you are familiar with this term, it is also known as the hypervisor, or sometimes it is also called the virtual machine manager. All right. So this middleware is essentially responsible for all administrative tasks. All right. So that is the architecture of computer clusters. So now if you do this, right, if you build an architecture like this, and of course there are challenges, and we will discuss these challenges, but if you are able to, let's say in an ideal situation, build this computer cluster, are able to implement this notion of single integrated computing resource pool. Remember back then when this started, this was not a trivial task. This was very difficult to collectively bring everything together under the roof and give a transparent view to the users. Cloud computing essentially perfected it later on, okay? If you're able to do all of these things, then you will have good scalability in terms of high performance jobs, okay? Not sequential tasks. Sequential tasks are sequential in nature, nothing to do there. But for parallel tasks, it will increase the availability of resources. All right. Now, depending on the type of job that is being submitted to these workstations, if the commodity hardware, which can be easily added to the network, right? They're everyday PCs and workstation, right? They're not supercomputers. You can even take a laptop in today's day and age, and you can add that to a cluster, right? It's that easy. All you need to do is just plug it into a switch, okay? So that will increase the availability of resources, all right? If there are multiple resources that is available, which are maybe similar in nature, and sometimes they're also dissimilar, but essentially they're available, that is the important thing, then it also increases the capability of fault tolerance, okay? And fault tolerance, when we talk about increases the capability of fault tolerance, then this is basically achieved through replication and or duplication. Okay. And then it allows for modular growth. Okay. If you understand the concept of modules, think Lego bricks. Right. So what happens when you're building a Lego? Just take a piece, add it to the existing puzzle. Right. If you don't need that piece, you just remove it from the puzzle. It's that easy as it is, right? Just plug and play. So that is what this particular architecture allows us to do as well. If you want to add a particular physical resource to this, physically connect it to the switch, get it online, and then register it with the middleware and let the middleware take care of it from that point onwards. It's that easy. And if you don't need it at any point of time, then you can just remove it. In contrast to this, if you think of that same idea of modular growth for previous high performance computing architectures, which was using supercomputers, you cannot just simply bring the supercomputer, just add it, and boom, you're done, right? It's very difficult, right? So that's where this whole idea is coming from, okay? And the way that all of this was supported was through the utilization of community hardware and software. That is everyday hardware and software that was available, not using anything that is too specialized or difficult to execute, okay? But of course, it wasn't without challenges, right? So one of the challenges that was there is faster communication. Remember, these were all connected by the switch, right? So even if, of course, if they are geographically dispersed, then it is a no-brainer to talk about the fact that there is going to be some form of latency that is going to be present. If you are connecting, even in cloud computing right now, this is still an issue, is that, let's say if you decided to take a server and then put it, let's say you are here and the nearest data center for Amazon here is Ohio, okay? For some reason, let's say you decide that, oh, I'm going to put a server in Tokyo. Without, of course, it would make sense to deploy a server in Tokyo's data center if you have too many clients in Tokyo in order to reduce the latency. But let's say you don't have any clients, you're serving the Americas and you decided you put it in Tokyo, right? You can do it. Nobody's going to stop you from doing it, but that's going to affect the latency, right? But that is a no-brainer. The problem when these computer clusters were built is that even if you have a very large room where the interconnectivity between two different devices requires a larger length of the wire, even that has an effect on latency, okay? So that is something that you have to kind of keep in mind, right? So, okay, so there's another question. What is the difference between replication and duplication? Would somebody like to take this question? This should be something that you should be aware from the database course, and if not, from other courses. Would somebody like to contribute to this question? What is the difference between replication and duplication? Anyone? No? Come on, think about it. I'll give you 5 minutes to think about it. All right, look it up. If you don't know, look it up.
I think the concept is that like duplication is an exact copy, whereas replication is like identical to the copy. Like there might be some variation.
Okay, that's a good start. Would anybody else like to contribute? It's right along the right directions. Need a little bit of support to that explanation.
I think to piggyback off of Sal, I'd say replication is more of like reproduction almost, like they're making it over.
And duplication?
And duplication is just the exact same thing.
Duplication is done generally for data probably, and replication is done for some kind of environment.
Okay, but do note that in databases, you do both replication and duplication. So then what's the difference there?
Is replication recreating and duplication is just copying?
Isn't replication more of a live operation? Duplication is just like you just duplicate it. Replication is always you're backing it up all the time, replicating it.
Right. So inherently, that's right. The last two completed the initial explanation that's algae. So what is happening, it is not about just data and then something else. It can be applied to basically, it is mostly applied to data only, because at the end of the day, you don't want to back up your processes as such, which is up and ready and then executing, right? What you modify is basically data, right? So if you're creating duplication, right, or if you're performing duplication, this is only for backup purposes, right? So if you want to restore something, you restore it from your duplicated copy, right? You can create checkpoints and then you can duplicate your entire system, whatever your system is. You can create a system image if that is what you want. Replication is something that is used for operational purposes, okay, in order to achieve consistency without trading off on availability. So essentially what it means is that, let's say you have a copy of a database table, right? If at a certain point of time, you want to, if two users are using it and they're using the same table, in order to prevent one user from overwriting the content of the table and whatever modifications the other user is doing, then you have to wait for the first user to finish its activity and then allow the second user to kind of chime in, right? So this affects the availability, right? But this is done in order to make sure that the integrity of the database is preserved, right? So the database is not updated. So in order to increase the availability, in order to allow both of these users to kind of work or access the resource that they're trying to access, what you can do is you can replicate this database table and give each of these users a copy. Both are copy at the end of the day, but one is for operational purposes. And then this user, the second user, works on their copy, and the first user works on their copy. And then these two copies are merged together and then make sure that the integrity of the database is not violated, right? And this is basically where the notion of replication is useful, right? And then duplication is basically just taking this whole table, and let's say at the end of the week, you have a checkpoint every week. Let's say you're a weekly checkpoint. You're just creating a copy of this entire table and then storing it somewhere else. So in the event that there is a crash of the database, which is essentially what fault tolerance is all about, you have to tolerate the fault that happens in your system. Then you can take this duplicated copy and then restore it. Okay, so that is basically the difference between replication and duplication. All right, but boiling it down, at the end of the day, they are both copying the data. That is where the confusion, comes from. But how you use them, that is completely different, right? And that is where the differences come from. All right, so that is something that you want to keep in mind. All right, so communication is an issue, as we talked about, even for the resources that are not geographically separated from each other. The other question is about scheduling. If you have taken any courses on distributed computing, right? By the way, this course is actually a combination of computer architecture and distributed computing, and a little bit of distributed OS. If you have taken distributed OS, you would have covered the algorithms of distributed computing as well. So that's why we're seeing a lot of this. That's where cloud computing comes from, essentially. All right. So, all right. Anyways, so job scheduling is also another issue, right? So let's say you have these 4 systems. Okay, just for our example, you have one parallel application which can be broken down into, let's say, 2 different tasks. You have another parallel application which can be broken down into 8 different tasks. Let's say you have another which can be broken down into 16. So now, which of these resources as a middleware, or which of these available resources will the middleware schedule these tasks to, right? And this is, if you think of the bare bone problem that this refers to, is the fact that there is a problem in algorithms. I don't know if you have taken an algorithm design course, then you must have done this. So let's say if you have P1 to PK processors, and let's say if you have J1 to JN jobs, okay, how do you schedule these jobs depending on the fact that you want to maximize the number of jobs that are allocated, but you don't want to violate the constraint about, let's say, the n number of jobs per processor that can be supported. Something like this. Or there can be another constraint where you also want to minimize the completion time of the jobs that you are basically allocating, right? So if you notice here, if you read between the lines, if you don't remember this is a job scheduling problem, and this is one of the quite a famous problem when you are learning design and analysis of algorithms. You essentially need to figure out how do you do this scheduling, and this is not a trivial task again, because that goes into the problem of optimization, depends on the type of optimization algorithm you're using and stuff like that. So it wasn't as easy when it came into being. Now, right now, there are some standardized protocols to figure out with respect to the load balancer as to which processors will get what kind of tasks and how you're going to schedule them. But this is also, scheduling is something that is still ongoing, right? Even if you search for research papers on this right now, you can find research papers on scheduling. They're still there in different shapes and forms, but it's a problem of scheduling. The third major problem was the single system image, right? Remember, interconnecting them is not the end of the task. It is to make sure that the feature that needs to be facilitated by this kind of architecture is basically the single integrated computing resource pool. That is what we're talking about, is we need to implement transparency for the user so they don't see this as different commodity hardwares. They see this as a single PC that is available to them, right? So again, we discussed that to implement that, we need to implement the notion of what is known as a single system image, right? So that is one of the biggest challenges. We will talk about what that entails and what are the properties of a single system image that will be implemented. And of course, we need to ensure that there is high availability. Because we said that if we build this architecture, we will get high availability. But then you should question yourself, is then why are we saying again that in challenges, high availability is a challenge as well as a benefit? And the reason behind that is because it is community hardware and software, and at the initial days, people were pooling the resources that they had, right? So there was no assurance about the type of commodity hardware that was being added to the network. So that means I can take a very old laptop right now, okay, one of my initial laptops, which probably had like 512 megabytes of memory, right? I can just add that with 40 gigabytes of storage, right? I can add that, it will be accepted, right? But will it be able to support today's task? Maybe not, right? So it might crash, it might go offline, right? If you add a laptop, it runs out of battery, you forgot to connect it, it goes off network, right? It goes offline. What are you going to do, right? Those assurances were not present, okay? In this particular architecture, we're not talking about cloud computing, keep that in mind. So that is why high availability is also a challenge in addition to being a benefit as well, right? So when we are developing, or when we were developing these computer clusters, right, what we had to keep in mind is to make sure that any computer cluster that was developed should be scalable in nature. Then we have to determine its packaging, right? I will come back to this in 1 second, right? Then there was the question of control, which is basically administration. Then there was the question of homogeneity. And I want to pose these as questions: programmability, how they will be, and then security, that is kind of self-explanatory, that how you're going to make sure that these are secure. So the reason why I gave question mark is because it's a question for you. What do you think, intuitively speaking, packaging means with respect to these computer clusters? Or you can take any of the other questions. What do you understand by homogeneity? And what do you understand by programmability? Go, whoever wants to take the field.
I would
No.
say it has something to do with how the clusters are put together for packaging.
Elaborate. Don't use the word packaging. You're right. You're on the right track. Just use a different word.
The individual machines, or to use your paradigm of attaching the laptop, how that is connected and interacts with the other computers that are local to it, and then the ones that are not.
Correct. Yes, correct. Homogeneity?
That would be whether they're the same or not. So kind of the same idea, but
right. So just to elaborate that a little bit, is that if this PC has the same compute powers, storage powers, as compared to this PC, whether they're running the same type of operating system or they're running different operating systems, So those are the different kind of, aspects that falls within the category of homogeneity. As packaging was mentioned, is that when you set up these computer clusters, okay, they're physically present somewhere, right? In some room, or they're distributed in nature, geographically spread across. So how are they set up physically? That is what packaging is, okay? Not with respect to the SSI, because that is on a software level. Packaging has to do a little bit on the hardware side, okay? Homogeneity is also a hardware requirement, and then programmability is basically how you tie that up to control, is how do you program these different clusters in order to let them support these virtual environments and things like that, okay? So these were basically the 6 different design criteria, and you can see this packaging, control, homogeneity, programmability, security, and scalability will essentially become the backbone of data centers. That essentially is the backbone of cloud computing as a service, right? So that is the reason why we are studying all of this, to understand that how this came into being, right, in the early days. All right, so scalability, straightforward. It's all about modular growth. How easily can you add more physical resources to the system? And if need be, how easily can you replace existing resources or remove them if you ever end up in a situation like that, right? So in the earlier days, the whole idea about physically, let's say you have 100 uniprocessors and taking that to, let's say, around 10K multi-core nodes, that was a very challenging task. Where would you get so many resources? How would you add it in a short period of time, right? How can you make that happen? Remember, we talked about the fact in that web server example for Black Friday, right? Just during that 2 period of time, if there was a 10-fold, 100-fold growth, and all you can do is support that through actual physical machines, then you would have to bring all of those 50 machines, physical machines that we talked about, to support all of those additional servers that you need, right? This was a problematic task, okay? And the solution, this is where the motivation of virtualization came into being, because the solution to that is that if you realize that, hey, if I have a strong system that can be further broken down, and then we can virtualize the resources and then use that as independent resources in itself, then I can take one physical machine and I can increment that to multiple virtual machines and essentially support my idea or notion of scalability, right? So this is where the seed of scale virtualization kind of lies within, which is basically the feature of scalability within computer clusters, the idea of computer clusters, right? But it wasn't easy even then, right? Because if you added more computers, then you will have to figure out what will be your network design, whether you're using a mesh topology, whether you're using a star topology, whether you have a bus interconnection, what do you want to do, which is better for you, right? There were a lot of discussion that was there that you have to kind of analyze in order to increase or scale up scale out the different physical resources that was available in the computer clusters, right? And of course, if you're adding more systems to it, then packaging would be a problem. That is, how are you going to set up, right? So packaging is right off of this. That will also increase, or that will also bring into the question of power consumption as well, right? Power consumption is a thing that goes hand in hand when you scale out, right? That is when you add more resources, right? So for example, all right, so in addition to power consumption, if you are adding more and more machines to a single room, right, that also requires you to ensure that these systems are kind of, they remain at a certain temperature, right? I don't know if you have ever had the chance to visit a server room or like a data center room, but it is cold in there, right? It is very, very cold, because if that cooling goes away, try to visit if you ever get the opportunity. You'll realize how much cooling is actually required to maintain all of these server rooms. So if you keep on adding more and more system resources, then you have to invest more and more in the cooling. Cooling again kind of directly goes back to power, and then power kind of relates back to cost, which is one of the most important operational criteria that you have. Now, in addition to this, there is also the problem of the limitations of memory, depending on the type of hardware that you're using and the processor architecture that you're using. how much disk input output you can do. Inherently, disk input output is one of the slowest operations that you can encounter when it comes to computer architecture. And then what is the threshold of latency that you're willing to tolerate for your application and still be able to implement your architectures, okay? When it comes to packaging, there are two different options that are available to you. The first one is known as compact clusters, okay? Which means that all you have is basically different PCs, okay, that are set up side by side on shelves. We call it racks, okay? And these PCs are just directly connected to the switch. So all they have is basically a LAN connectivity and then a power connectivity. And then this one goes to the network switch and the power goes to the power, and they're set side by side, okay? So if you've ever seen an image of a data center on Google and stuff like that, you will see these large shelves that has all of these machines just stacked on top of each other, right? If you kind of recall that, then that is what compact cluster setup architecture basically is. That forms basically the backbone of these modern day data centers that we have. The other type of packaging is known as slack clusters, okay? Since this was a packaging for clusters, that's why we have the cluster naming, where for every computer, you just don't have the power and the switch connection, but it also goes to the mouse, okay? And it also goes to the keyboard. It also goes to a PC screen and things like that, right? So that is basically a setup that is slack in nature, okay? The slack setup. So essentially, these compact clusters, typically, given the nature of the setup, they will be sitting in a particular room. And we call a room basically a server room or a data center room and things like that, all right? Whereas slack clusters are typically going to be located in different rooms, because if you get an understanding of the discussion that we're having, right, these machines are individually owned. There's a good chance they're individually owned, right? So they can be present in different rooms, different buildings, or different regions altogether, right? It could be distributed in nature. Not centralized, decentralized, that's a different question again, but they are distributed in nature, okay? And typically compact clusters will be centrally located somewhere, all right? So what impact this has, the packaging, is basically on the communication wire length. If they're closely packed together, then the distance that you have to cover in order to connect, let's say, these 4 nodes versus all these individual nodes is going to vary, right? And if you use a communication wire length, which is quite large in size, then that is going to also have a proportional impact on the latency of connecting these computers, okay? Control is another issue. And now this is where the administrative part comes into the picture. And you can have 2 types of control. You can have centralized control, you can have decentralized control. Typically, not all the time, when you have a compact cluster, then the go-to approach of control is centralized in nature. That is, all of these different computers will be connected to a single source computer, which is going to be your administrator. And that administrator will be running softwares that is responsible for monitoring the health of all of these different computer cluster or computer nodes that you have in a given cluster, okay? The other option for control is basically decentralized in nature, okay? Where the autonomy of control is with the individual node itself, typically. So again, generally speaking, not all the time, for slack clusters, you have decentralized control. That is, the individual owners who contribute their resources to the computer cluster, they are essentially responsible for managing their own individual nodes, okay? Then there is a question about homogeneity. And homogeneity can be, well, either homogeneous or heterogeneous in nature, okay? And it's kind of straightforward. Homogeneous clusters, they're all using the same platform. They will have the same processor architecture, the operating system, and all of these will probably come from the same vendor, okay? So it, to an extent, becomes proprietary in nature, but it helps the interconnectivity a little bit, right? Not a little bit, it helps it quite a lot, right? You don't have any issues. And then if you have a heterogeneous cluster, which is typically the case when we are working with slack clusters, okay, or clusters where the control is different, the location is different, then we get into the problem of interoperability. Now, this is a problem that right now cloud doesn't face anymore. It used to be the case 2009, 2010, there was a lot of research, but now it's no longer a problem. This problem now is quite present in the domain of Internet of Things right now. Okay, so there's a lot of issue because standardization has not yet been cemented in IoT. So you find a lot of different devices from different vendors, and everybody is trying to connect these different devices together. The network protocols are different and stuff like that. So anyways, the main problem of interoperability is the fact that since you have different platforms, and if they're all collaborating collectively, right, in order to satisfy the requirements of a particular task, and the task requires a certain platform, then how do you meet that, right? How do you make that happen? So a very simple stick example that you can think of here is that if I take this cluster that was present in that previous diagrams, right? Let's say if I have 4 nodes, the setup of these nodes is, the packaging of these nodes is Slack in nature, and the control of these nodes is, let's say, decentralized. Okay, let me just say decentralized. And you have a middleware on top of this, which is basically going to act as your hypervisor or responsible for kind of giving this transparent outlook to your user. And the user comes, submits a job request that requires a Windows platform. Okay, let's just ignore for the time being. Let's just assume that storage and memory is available with all of these nodes. And this is Windows, this is Windows, this is Mac, this is Mac. Right? And this is a problem now, as you can see, that you have 4 resources collectively, but due to the problem of interoperability, you can only use these 2 resources. Right? So that kind of diminishes the idea of efficient resource utilization. Right? So now, even if we think of scalability, if I add 2 more Mac nodes, right? If there are 2 more users, individual users who come and donate or contribute their Mac platform, this is really not going to help the situation of this user, right? As a middleware software, I can't really utilize it. Or can I? What do you think? So this is a completely parallel program, let's say, a batch processing task. And let us just say, for the sake of discussion, this can be broken down into a minimum of 4 tasks, 4 parallel tasks. Okay, but however, right now, looking at this discussion that we're having, since there is 2 Windows-based platform that can execute this task, that means, and let's say each of these tasks takes, let's say per task, it takes 3 unit time. Okay, so what I can do as the middleware, since I know that these are not suitable platforms, I can do 2 tasks at a time. Each of them will be finished in 3 unit time. And then I will need another 3 unit time to finish the rest of the task, which will be deployed once the initial tasks are done. Okay, so the total unit time that is taken is 6. However, in the best case scenario, it should take just 3 unit time because these are all parallel tasks. This should all be able, and I do have the resources. Let's say I have 1, 2, 3, 4, 5, 6. What is this? 4 and 2, 6 resources, right? But then you have a problem. So yes, these.
So I have a question. Since like it creates this interoperability issue with like cloud computing specifically, when would you like need to have a heterogeneous cluster? Why don't you always just apply homogeneous cluster?
Okay, so you cannot dictate who contributes the commodity hardware and what kind of platform do you have. You see the discussion that we have, you don't choose your platforms. So what I'm trying to say here is this particular architecture, right? People can contribute their resources to the network. Okay, so essentially in that situation, forget cloud computing for a second. This is not for cloud computing. You have to understand how cloud computing came into being to solve the problem that was there, right? And that is where we're going towards. In computer clusters, people could collectively contribute whatever resources they have to a network. Let's say I take my computer and 3 of these students here, and I built up a computer cluster, right? I cannot tell the students who decided to join my network that you need to bring a Windows machine. You see what I'm saying? If they come, yeah, cloud computing solved this issue, and we will get to that. But you need to think about this. You all need to think about this. Is like, if I just use the physical resources that are available to me right now, the best I can achieve for this task, which can be broken down into 4 individual tasks, is around 4 unit times, 6 unit times, right? Best case is 3. How can I achieve that? If you can think through this, you will understand what cloud did and why it did it.
If we can do like the virtualization within the same Windows system.
Oh, okay. So that's one way of doing it. But there is another way. Virtualization can also be done on the platform that is
the Macs.
The Macs. Yes. I can create a virtual environment. Remember, when we were discussing virtualization, I said that I can essentially, let's say, inherit, but utilize some of the resources, available resources that is there in the underlying. Okay. When I just say underlying, just think of the actual physical machine. Okay. And then I can decide what this platform is going to be, what OS I want. I can already decide based on the available resources, how much of memory and storage it requires. And then I can deploy the application there. I can do that. And this is where people understood that virtualization is not just about, utilization of idle resources. It's more than that, right? It also is capable of addressing certain issues that would have been there if people have not adopted that notion of that concept, right? So that is where people started to understand that it's important. Of course, if you need Mac, you need Mac, right? You don't want to run a Mac within a Windows. If you have the Mac, you can run it on the Mac. That is always good, right? You don't have to create sandbox environment. The other operations, there is another notion that people solved, and you might be familiar with this as well. Let's say now, for this particular task, okay, these 4 individual tasks for this one job, right? It requires a set of third-party softwares, some kind of dependency softwares, and things like that. Okay, so that is doable in one way. The installation, we all know, Windows has one style of installation, Linux has one style of installation, Mac has one style of installation. So every time you try to deploy one of these tasks to a particular environment, right? Let's say we're having a different discussion right now. Let's say the jobs are suitable for Mac and Windows as well. But the discussion that we're having right now is that these tasks requires dependency softwares that needs to be installed. And the process of installation is different for these environments, right? The same thing, okay? So if that happens, every time I allocate a job here, I being the middleware, am responsible for setting up the system. And that is a tedious task because I have to go through different processes to achieve the same thing, right? How do you solve that? How do you make sure that you don't have to go through the cycle of installing dependency softwares and stuff like that for different platforms, following the platform's way of installation? How do you speed up this process?
By finding a common ground between Macs and Windows, which is basically interoperability.
Yes, elaborate a little bit. Script, yes, scripting will be required. That is true. But how can I make it more efficient? I know what are the pieces of information that I do have here. I know that, okay, it requires Windows, but it can also run on Mac. It requires, let's say, 15 different dependency softwares, right? So what I want to achieve here is that instead of going through the cycle of installing it, depending on the platform for every system where I deploy this individual tasks to. So how many times do I need to do the installation? If I deploy this 4 tasks to 1, 2, 3, 4 systems, how many times I am installing? 15 times 4 is?
60.
60 times, right? But I want to do the best case scenario. That is, I want to just install them once.
I install them on the cloud instead of installing them on the devices of the end users.
Okay, so these are not end user devices. Think of these as the cloud itself for a second. These are machines from the cloud.
Can you make one image of a VM and deploy it to all of the machines?
Yeah, what is it called? Does anybody know what is it called? It is. You create a VM, create a virtual machine, install all these dependencies.
Docker image.
Okay, so Docker is the software that implements this.
Containerization.
The notion, the idea, the concept is called containerization. That is correct. Okay. So containerization is implemented by a software called Docker. It can also be implemented by, for orchestration purposes, it can be also done by Kubernetes. I think I misspelled this, but you get the idea. And then what happens is that you create a VM that is basically a container. You install all these dependencies, everything that is required for this task to run, and then you deploy this VM itself on these machines, right? So when they deploy it, you don't have to worry about installing the dependencies or the platform that it is running. Everything is present in a single integrated resources. That is also a concept of cloud computing, right? But the reason how it came into being was addressing these challenges that was realized when working with computer clusters. That is basically the drift of this discussion, right? It's not that we are not just learning about cloud computing, but we are trying to appreciate that why things are the way it is and where it came from. If you don't know your past, you cannot appreciate why some things are working. Okay, so that is one more concept, that is cloud computing solved it, and it kind of originates from this operability problem and dependency problem. Security is always going to be there. But this security discussion that we are having here is with respect to specifically communication. That is how communication happens from a networking point of scenario, right? And the communication between these computer clusters were categorized in two different sections, right? The first one was basically your communication can be exposed. The benefits of that is that you can use the existing routing protocols that was out there in the internet, right? You can use TCP/IP and stuff like that. But the problem is, of course, it was easy to implement, but it would still be less secure because you're now exposing your computer cluster, your interconnectivity of your network to the outside world, to the World Wide Web. And you know how that goes, right? So if you have an open port, well, people are going to poke it and see what happens, all right? This is also going to create a problem with respect to the latency and interruption because people from outside may be communicating, they can be communicating from far off places. There can be unnecessary communication that may be received, spam communications can be received and stuff like that, okay? Although you can implement it really fast. That is the benefit of it, right? The other side of it is that if you don't want to expose your communication of your interconnectivity, then you have to build your own networking protocol. That is, what kind of routing protocols are you going to be using? What are your alternate routing protocols in case your main routes fall down? You have to maintain your route tables, and all of these things are going to be your responsibility, right? The problem at that point of time was that there was no standardization with these communication protocols. So that means if somebody did build a own proprietary computer clusters, let's say HP built one, right? Then if HP has to manage the whole networking protocols, that was a really like a uphill task at that point of time. Something happens, you will have to maintain it. There was no support or resources available for the work, right? So this led to two different types of clusters altogether, right? Depending on these features that we just talked about with respect to scalability, packaging, control, homogeneity, and security, essentially the clusters that was built can be broken down into two different clusters. So the first one is known as dedicated clusters, okay? And the second one was known as enterprise clusters, all right? So dedicated clusters essentially used compact packaging, okay? The control entity was centralized in nature. So that means the administrator was centralized, and essentially it was used for either interactive or batch jobs. So interactive basically means day-to-day job that interacts with the client, and batch jobs means jobs that run on the backend, passive in nature, doesn't require any kind of user input once it is submitted, right? So it focuses both on throughput depending on the nature of the task that you're doing, and it can also focus on improving the performance, reduce the latency, and things like that. The other one was enterprise cluster, which is also known as sometimes business clusters and stuff like that. The goal of enterprise clusters was to utilize the idle resources that was sitting in the enterprise. So you know the fact that, let's say, our university has a lot of computers in the labs and stuff like that. Are these computers being used all the time? No, right? So if the goal of the university is to, let's say, utilize those resources that are just sitting there, right? Then that led to the motivation of enterprise clusters. Business clusters decided to do And typically, these are heterogeneous in nature. Not all labs will have the same machine. If, let's say, they allow the employers, not employers, sorry, the employees to kind of contribute to this cluster, then they will contribute it by the form of their own machine, which may not be the same, of the other machines that exist in the clusters, right? You can have different branches of your company in different geographical location, and as a result of that, your clusters will be distributed in nature. So that essentially kind of leads to a Slack cluster packaging, okay, which can be centralized in nature, or it can be decentralized in nature, okay. And of course, for both, the computing is distributed because you're distributing the computing that is required to be executed across all of the physical resources that you have, right? So we don't worry about that. But the one niche problem that was present in enterprise clusters is that if there is a local job running on the machine, then that takes priority over the enterprise job. So what that means is that if my machine is a part of an enterprise cluster and it is running one of the tasks for me that I have executed on my machine, that takes priority over any kind of group task that is assigned by the middleware to all of the clusters. Once my task is over and then resources are available to execute the enterprise task, then that takes preference. Okay, so local takes preference over the global or the enterprise jobs that are out there, right? So at this point, the question, and this is the last discussion that we will have for today's lecture, is when would you choose to, if you were the designer, the computer architect, okay, when would you choose to go for a dedicated cluster versus when would you choose to go for an enterprise cluster? What is your decision making based on it? Come on, think about it. Is the question clear?
I would think that it would be a matter of how often you need to do something computationally complex.
Okay, let me write that down. So, how often do you need to do computationally complex tasks? Anything else? Think about it. This is basically a problem of decision making. And I'm asking you to think from a factual standpoint, or not factual, sorry, from a scientific standpoint, is how would you come to the decision of what is the best solution of architectural design for your organization? Of course, no doubt, this is subjective in nature, okay? And it needs to be evaluated on a case-by-case basis, right? So there is no universal answer that you should use dedicated in such scenario and you should use enterprise cluster in such scenario, right? That is the reason why I'm asking you to think is that how would you come to this decision-making process that when should I use a dedicated versus an enterprise cluster? What is the basis of your decision-making? Somebody
The
asked you. Yeah.
number of users that we have to serve.
Okay, let me write that down. Hold on. So this first point, number of users to support. What else?
My point was to add to the first point, because you have like heavy users and light users. And you need to know the number of users you're going to serve. Yeah.
Okay, together. All right, what else?
How you're administering it, like if you're having it be essentially administered. And I guess also the deployment scenario, like if you want to fully utilize all the resources versus, devote everything to a single virtual host to do a certain task.
Okay.
And have that granular control of a dedicated, just depending on if you're maybe a cloud provider, you'd want to utilize all the resources of an enterprise cluster. And you might, if you're a researcher, you might want to dedicate a cluster. That's how I'd see it.
Okay, good, good, good. What else?
It's gonna come down to how much money you have too.
That's
It
also.
will. We need to start from there. Money. Anything else? Or cost? So let's not put it in a little bit more shape. Let's whip it into shape a little bit. Okay, I'll go a little bit over time if that's all right with you guys. Do you have any class right after this?
I
Yeah,
do.
5 minutes. Do you have 5 minutes?
Yeah, sure.
Okay. All right. So let's put it in a scientific perspective. We know that cost determines everything else from a company's perspective, right? So this is a business. We're not doing this for fun, right? So if I don't have the money for it, I cannot do it. Now, how do I translate that? How do I figure out the requirements, that is this, and then kind of draw some equations out that can help me tie up these factors to the money? Okay, so I will leave you with this question, and I will ask you this question when we meet physically, and maybe some online students can also join. I will still be doing the Zoom call, okay, as to how we can do this, right? So again, to reiterate the question, to help you understand, these are all of the factors that was just, given from the floor, which plays a role in deciding whether you should go for a dedicated or enterprise customer. That is correct, right? Subjective in nature, not a problem. But we also know that for any organization, whether something can or cannot be done depends on the budget that that organization has. So the discussion that we should have right now, and you should be able to think for yourself and come to the conclusion, of course I will help, is how do you take all of these features, which are not in form of an equation right now, and then tie it up to this cost. Okay, so I will stop here, and we will continue this discussion the next time we meet in person on Monday, okay, the coming Monday. All right.